Hey guys, and welcome to lecture 3 on my mini text series lecture on special relativity. And we're going to continue from where we left off discussing Einstein's fix on relative velocity. And so the way that we're going to walk through this, we're not going to go through any sort of rigorous derivation or sort of how Einstein arrived at the exact equation. We're just going to kind of state it and explain why it works and how it works. And then I have some examples that I'll walk through of how to use it. So let's remember that the case for why we want to use Einstein's modification is because if we were to use the Galilean velocity relation, we would see that if the velocity of a particle or object p with respect to a moving reference frame s bar is equal to c, then we can't actually get the answer that we would deem correct by Einstein's comment or theorem that regardless of relative motion between observers, the speed of light is constant. So basically, we need to figure out a fix to this. So what I'm going to do is I'm going to draw a little diagram of just how to kind of view what we're looking at. So we have x, y, and we'll say this is reference frame S. And then we have a copy of this that we say follows x prime, y prime, and we say that it's moving at a velocity, we'll say u s bar s. And then we can say that we have a particle or object or point p, whatever you like to say, and we say that this is moving at velocity c. And so how do we make sure that if the velocity of that point particle in a particular arbitrary reference frame moving with respect to a fixed reference frame is the same to all observers? Well, Einstein said this. So we'll say Einstein's velocity relation is this. So we have the velocity of some object or point A with respect to a fixed reference frame S is equal to this. And voila. So without going through too much rigorous derivation or anything like that, I'll just kind of explain how this works. So again, we have the velocity of a point A in reference frame S, the fixed reference frame or the ground observer, is equal to the velocity of the object in the moving reference frame S bar plus the velocity of the moving reference frame with respect to the ground observer. So think about that train example. And then in the denominator, we just have this factor here, where we have 1 plus the velocity of object A in the moving reference frame multiplied by the velocity of the moving reference frame with respect to the fixed reference frame over c squared. Now, how do we know for sure that this works? Well, let's try it out. So if I were to say if the velocity of this object A and the moving reference frame S bar is equal to C, and then the velocity of the moving reference frame with respect to the fixed reference frame is just some arbitrary U, we plug this in and then let's see what we get. So we have U AS is equal to 1 plus U AS bar U S bar S over C squared. We have U A S bar plus U S bar S. So after plugging in terms, what we get is we have 1 plus U divided by C in the denominator. And then in the numerator, we have C plus U. But then, if we divide both sides by C, we get this. So then we have 1 over C plus U over C squared. And then we have 1 plus U over C. But if we take a closer look at the denominator here, we notice that we have a common factor of 1 over C. So what we can say is that this is equal to 1 plus u over c over 1 plus u over c. And then since we have that factor of 1 over c in the denominator, we can multiply by the reciprocal and therefore have c here. And then we have UAS is equal to c, because this term here just goes to 1. And so here, it works. So that's exciting and that's great news, because now Einstein basically figured out the right modification to explain how we can compute a velocity between reference frames, or relative velocities between reference frames, while still maintaining the condition that the speed of light must be constant to all observers. So, with that being said, let's step into some examples. So these examples I am pulling from Griffith's introduction. I'll just write intro for short. Introduction to Electrodynamics. Chapter 12. And so if you're following along, you can find these problems and sort of work them out yourself, and just kind of follow along there. So looking at this first example, we have, suppose you're running at half the speed of light down the corridor of a train going 3/4 the speed of light. What would your speed be relative to the ground? Well, this is pretty simple. So first, let's go ahead and write out Einstein's velocity relation. So we know that the velocity of this person with respect to the ground is going to be equal to the person with respect to the train, the speed of the train with respect to the ground, or c squared. And then we have u of the person with respect to the train plus u of the train with respect to the ground. So now what they're telling us is that you're running at half the speed of light down the corridor of this moving train. So your speed with respect to the train is therefore equal to the speed of light divided by 2. But then what they tell us is that the train itself is going at 3/4 the speed of light. So the speed of the train with respect to the ground is then equal to 3/4 c. So then if we just kind of write out the different terms, so we have c over 2 plus 3/4 c. And we have 1 plus. Now, let's just keep in mind, because we're multiplying these two velocities and both of them have a c term in it, the c squared in the denominator will cancel out. And so what we'll end up with is 3/8, right? So just checking my math here. So we have 1/2 multiplied by 3/4. And so that gets you 3/8. And so then what this will equal, so we'll have 1/2 plus 3/4 multiplied by c. And so what that gets us to is 5/4 in the numerator. And then in the denominator, we have 8 over 8 plus 3 over 8. So that gives us 11 over 8. And so, and then we multiply this by c. Now, if we want to get the 8s to cancel out, then we'll have, or the 8 in the denominator to cancel out, or have a simplified term. We'll have 10 over 8 over 11 over 8c. And what we get is that the velocity of u with respect to the ground is then equal to 10 over 11c. So you're still traveling less than the speed of light with respect to the observer. So even though, with respect to the ground observer, so even though, you're at the super high speed and the train that you're on is still traveling at a high speed, you're still not, it's really hard to achieve going greater than the speed of light. And that's kind of what that denominator term in Einstein's relation is meant to prove. So I hope that was helpful. I'll box this out here. Now we'll move to the second example. So prove using equation 12.3 in the book that if the velocity AB is less than C and the velocity BC is less than C, then velocity AC must be less than C as well. So I'm just going to write out here that equation 12.3, just to make sure I'm not reading the wrong thing. So I always have the textbook open typically. So 12.3 is Einstein's velocity relation. So I'll say Einstein's. And they want us to write it in the following way. VAC. So basically they want us to prove VAC is less than C if VAB is less than C and VBC is less than C. And we're going to write out the equation like so. So we have VAB, VBC over C squared, VAB plus VBC. So now let's just kind of look at this component wise, right? So let's look at the numerator first. So let's just set some bounds on the relation here. So if VAB and VAC, or I'm sorry, not VAC, VBC is less than C, then VAB plus VBC must be less than 2C, right? Because at maximum, and this is something that can't be reached, but at maximum, both terms would be equal to C. And so since they're strictly less than C, then they must be less than the maximum value. So we have that written out. And then in the denominator, if VAB and VBC are less than C, so I'll just kind of write the quotes here, then we have that 1 plus VAB VBC over C squared. This term here must be less than 2. Now let me explain. The reason why is because at maximum, VAB and VBC are C. And so therefore, the maximum that this term it can't be this, but the limit, the upper bound would be 1. And so therefore, if we already have the constant 1 in front, 1 plus 1 is 2. And then because this term is strictly less than 1, then this whole term must be strictly less than 2. So then looking at the expression in total, we have VAC equal VAB plus VBC plus VAB VBC over C squared. Now, if we look at this term and we look at what we sort of deduced before, right? Sorry, I'll put 2 here. Now, if the numerator is strictly less, if the numerator over here is strictly less than the numerator on the right-hand side, and the denominator is strictly less than the denominator on the right-hand side, then the term on the left must be strictly less than the term on the right. And what this is saying is that VAB plus VBC over C squared must be less than C. And so therefore, we've now proven that VAC is less than C. So those are just 2 examples that help illustrate how we're supposed to view this equation. And that's kind of in the second example that we had here, the interesting part is the fact that, we were actually able to observe that Einstein's relation fundamentally allows us to limit the velocity with respect to any ground observer, regardless of how fast an object is moving in a moving reference frame, no matter how high the speeds. we still will not see anything achieve a speed of light greater than c. And so that wraps up our section on Einstein's fix. And moving back to our agenda here, what we'll go through next is the Lorentz transformations. And so the Lorentz transformations are going to help us describe the relativistic mechanics using the geometry and structure of space-time. So this is where we're going to start introducing a bit more abstractive concepts, but it'll be a lot easier for us to do these sorts of calculations when considering relativistic effects. So thanks for joining. See you guys in the next video.